Hello everyone, I'm Yuning.
安思明。
We will be going to share with you our research titled Network Formation and Interaction Patterns in a Statistics Classroom that we did under supervision of Dr. Umar Rabat. To understand students' interactions with peers, we collected data from a statistics course with over 200 students enrolled and applied social network analysis and exponential random graph models. We first introduced the content of methodologies, which include network visualization, network and node attributes, hypothesis testing, and ERGM modeling.
So this is our data. We clean our data to come up with source target list for student interaction and student perception of strong students in the classroom. And this is the first visualization we did. Firstly, we visualized the interaction of students in week 6 and week 9. We connected each student by edges. These edges are considered as bidirectional, which means if student A identifies student B as meaningful interaction, then automatically student B has interaction with student A. The size of the dot in the graph represents the number of interactions the dot has in the class. From the visualization, it's clear that the interaction in week 9 are denser, meaning the students interact with others more in week 9 compared to week 6.
In terms of social network analysis, there are two broad perspectives that examine network interactions. The first one is network level measurements. We've provided the formula for each measurement in the slide. Density offers insight about the overall cohesion of a network. Diameter measures the network level connectedness and captures the span of a network. In our datasets, we find that even though the diameter of week 6 interactions is much larger than week 9's, it has relatively lower density on average. Degree distribution captures the structure of the network. We can see that they are highly asymmetric, which means most of students have low degrees. The second perspective is node level measurements. First of all, degree of a node is the number of interactions the node has and can be thought of as a measure of popularity. Week 9 network has a higher average degree. Betweenness centrality focuses on whether nodes serve as bridges in the shortest path between two nodes. A higher betweenness indicates that the node has influence within a network. In our data, week 6 network has higher average betweenness. We also utilize eigenvector centrality and closeness centrality in our analysis. Next, we use hypothesis testing to compare the social network analysis measurements in different periods of time. We compare the degree and betweenness of two networks by paired t-test. We found strong statistical significance between both node degrees and betweenness of week 6 and week 9 networks. This means the number of interactions in week 6 on average is less than it in week 9, and there are differences in week 6 and week 9's betweenness. Next, we focus on the relationships between students' grade, both midterm grade and final grade, and their perceptions of strongness from peers. Perception of strongness means that if student A perceives student B as mastering course materials strongly, then the perception of strongness of student B will increase by 1. We use Pearson correlation tests to measure potential linear correlation. From both tests, the p-values are lower than 0.05. Then we conclude that the correlation between perception of strongness from peers and students' grade is significant, and they show a positive correlation.
So exponential random graph model is a commonly used model in social network analysis. It's being used to predict the possibility of edge formation between two nodes. This is the general formula for ERGM. The log probability is formulated by the network statistics noted by GK here. The theta over here are the parameters we are trying to fit. We used the ERGM R package and chose network statistics like final grade level, gender, race, perception of strongness, etc. We use both node factor to explore differences between node connections and node match to explore the homomorphy of network patterns. These are the results from fitting the ERGM model. The edge density can be computed from the fitted model. Regarding grades, we found no strong evidence showing that students are more likely to interact with good grade or bad grade students, which is a good thing from an inclusion perspective. Interestingly, when looking at homophily, students with final grade C are more likely to interact with students with the same grade, while students with grade B are 3 times less prone to interact with students earning a final grade B. In terms of gender, one interesting result is that males are 1.6 more chances to interact with male students compared with other genders. Here are a couple of more interesting results. Students are 15 times likely to continue interactions throughout the whole term once they have initialized the contact since midterm. Students' interactions are positively correlated with the perception of peers as well, based on the p-values listed over here. Using Monte Carlo simulations of network generated for different parameters by ERGM model, we find that the change in degree, edgewise shared partners, and minimum geodesic distance of our data has been successfully captured by our model. Three main takeaways from our research are: first one, the perception of peers plays an important role in both academic performance and interactions. Second, students' interactions differ based on gender and their grades. Third, students interact more as the term progresses, but most students don't change the people they interact with since the midterm. And that's it for our research. Thank you for listening.